Alright guys, so what I'd like to do today is go over some of the homework problems that you've had this week and hopefully clear up any confusion that there might be on those problems. The first problem that I'd like to look at is problem 41. In this problem you have an object that's moving up an inclined ramp, and they want to find the ratio between the force of gravity and the normal force. So let's look. Here's our incline. Let's say this is theta. This is 90 degrees. Here's our object. The force of gravity acts straight down towards the center of the Earth. However, on inclines, remember that we rotate the coordinate system so that the x-axis lies along the incline and the y-axis is perpendicular to the incline. And then we said that what we wanted to do was to get a x and y component of the force of gravity. So here this would be the y component of the force of gravity, and the normal force would be the same magnitude as the force of gravity but opposite in direction. Let me erase that. So it would be pointing upward perpendicular away from the incline. So the force of gravity is pretty easy. It's just mass times gravity. We derived what the y component of the force of gravity was the other day. We said it was just the force of gravity times the cosine of theta. In this case, the normal force is also equal to the y component of the force of gravity. It's just in the opposite direction. If that wasn't true, then the net force wouldn't be zero, and the object would be accelerating up or down on the incline, and that's not what's happening. So the ratio here is the ratio between the normal force and the force of gravity, which is the ratio between the magnitude of the force of gravity, the y component, and the force of gravity. So that's just mass times gravity times the cosine of theta divided by mass times gravity. That all cancels out, and you see that the ratio is actually just equal to the cosine of theta. Okay, so that's the answer to 41. The next problem that I'd like to look at is 81. In problem 81, it's again an incline ramp problem. Okay, so we've got some angle theta. This is a 90-degree angle. Our object is on the ramp. In this case, we're applying a force to pull the object up the ramp. The force of gravity is still acting on the object straight downward, but we're going to again rotate the coordinate plane so that the x-axis lies along the incline and the y-axis is perpendicular to the ramp. That means that the normal force will be perpendicular to the ramp. It'll be equal but opposite in direction to the y component of the force of gravity. And the force acting down the incline is going to be the x component of the force of gravity plus friction, which in this case will be kinetic friction since it's moving. We're going to need to solve each of these things. The mass that they give us is equal to 205 kilograms. Theta is 30 degrees. The coefficient of kinetic friction is equal to 0.9. And the acceleration in the x direction is equal to 0.8 meters per second squared. And what we're trying to figure out is what is the applied force here. I can use Newton's law. The sum of all the forces in the x direction is going to be equal to the mass times the acceleration in the x direction. The net force here is going to be the force applied plus the force of gravity in the x direction plus the force of kinetic friction. And that's all going to be equal to mass times the acceleration in the x direction. I can start plugging in things that I know. For the force of gravity in the x direction, that was an equation we derived, and it was mass times gravity times the sine of theta, and it's going to be negative since that force is pulling it down the ramp. The other force then is going to be the force of kinetic friction. Again, that'll be negative since it's acting down the ramp, and that's mass times gravity times the force of the coefficient of kinetic friction times cosine theta. How I got that was the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. And we said that the normal force on an incline is actually equal to mass times gravity times the cosine of theta. And that was, again, an equation that we derived the other day. The x component of the force of gravity is equal to force of gravity times sine theta, and the y component is equal to the force of gravity times cosine theta. Alright, so we can set that equal to mass times the acceleration in the x direction. If I solve all of this for the force applied, which is what I'm looking for, then I'll get mass times the acceleration in the x direction plus mass times gravity sine theta plus mass times gravity times the coefficient of kinetic friction times cosine theta. Right? And if I plug in all of the values for that, I'll get the answer to that problem. The next problem that I want to go over is problem 44 from your homework. Problem 44 was in two parts, and it was dealing with an object that was on the ground on a level horizontal surface, and we're applying a force towards the left, and a force of static friction is resisting us. They give us the mass, which is equal to 57 kilograms, and they give us the coefficient of static friction, which is 0.65. The first thing that we need to do in this case is find the max force of static friction, which is just going to be the coefficient of static friction times mass times gravity. Once we do that, we'll be able to tell if our forces are too large for the force of static friction to resist. In part A, the applied force was 267 newtons. We can use Newton's law that the forces in the x direction have to add up to equal the mass times the acceleration in the x direction. If this object's not moving, it's not accelerating, and that means that the force of static friction plus the applied force has to be equal to 0 newtons. So that means that the applied force has to be equal but opposite in direction to the force of static friction. As long as the applied force is less than the max static friction, this will hold true, and if you check the equation up there by plugging in the values, you'll see that that is the case. The applied force is to the left, and it's 267 newtons, so the applied force was actually negative 267 newtons since it was to the left. So that means that the static frictional force is the opposite of that. It's 267 newtons. Part B asks you for the max static frictional force, and that's what you found earlier when you were checking to make sure that the applied force wasn't higher than that. Okay, so that should be both your answers for 44. The last question is problem 48. In this problem, you've got a car, and the car has some velocity in the positive direction. It slams on its brakes, and the brakes lock the wheels, so now it's skidding on its tires. That's going to give it an acceleration in the opposite direction, a negative acceleration, and eventually it's going to slow down. And what we're trying to figure out is what is the velocity after a certain amount of time. The values we know are that the velocity initial is equal to 16.1 meters per second. The amount of time that passes while the wheels are locked is 1.3 seconds. The coefficient of kinetic friction is equal to 0.72. We need to find the acceleration. Okay, so again, we can do this by using Newton's law, that the net force in the x direction is going to be equal to mass times the acceleration in the x direction. If I solve for the acceleration in the x direction, that'll be the net force divided by mass. For the object, there is no applied force, but there is a resistive force, the force of kinetic friction, acting on it, and that's the only force. And that's going to be negative mass times gravity times the coefficient of kinetic friction. We'll divide by mass. So again, you can see that we didn't need to know the mass of the car because that's going to cancel out. We'll get the acceleration as negative g mu k. We can use the equation that the velocity final is equal to the velocity initial plus the acceleration times time. Plug in what we know about the acceleration, and we'll get the velocity initial plus negative g mu k times time will be equal to the final velocity that we're looking for. If you plug in all the values that they gave you, that should give you the answer you're looking for. If you guys have any questions about the homework beyond what we went over here, just come see me after school today in the lower school science lab.